that mirrors this before. We did this a few months back when we first started talking about what were called congruent. When we first started talking about congruent figures. Back in the day, sometime in September, October, we said this. Remember when we started with what was called a congruency statement? When we had a congruency statement, that told us, well, in this case, it's a four-sided figure because there's four vertices, which means there's four angles. I don't know what the shape looks like, but all I know is it's got four sides. If I had 5 letters, it had 5 sides. If I have 3 letters, it has 3 sides, and so on and so on. What this congruency statement told us first semester was that it told us what angles matched up with what. Jackson, put it away, please. It told us what angles matched with what, and it also told us what side lengths matched with what. For example, we knew from a congruency statement that angle A had to match with angle W, B matched with X, C matched with angle Y, angle D matched with angle Z. That never changed. We also knew then that there were segments involved. So when you had the segments that were involved, you knew how they matched up. You knew that the first 2 letters had to match with the first 2 letters over there, and so on and so on. What winds up being different between what's called a congruency statement and what we're talking about today is called a similarity statement is that you don't have the equal sign. That's a similarity statement. A similarity statement has that single tilde, I believe it's called, or squiggly. Is she trying to make a joke? Emphasis on the word try. So you get this thing called it's called a tilde. I just call it squiggly, it's easier. When you have a similarity statement, what happens is 2 figures are similar. If all corresponding angles are congruent, which we already wrote because of the congruency thing, that doesn't change. But the other part of that becomes and all sides are proportional. Now, when you're talking about that word proportion, we said what that meant yesterday. When you have things that are proportional, it means that you have more than 2 ratios that are equal to each other. So in this case, if I've got 4 sides, I'd have to have 4 ratios equal. If I have 5, I'd have 5 ratios. 3, like a triangle, I'd have 3. What we do here to write out what's called that similarity statement is very, very easy. If we have this figure of A, B, C, and D, and I'm saying that it's similar to W, X, Y, and Z. When we talked about this before in terms of congruency, I'd say that AB is congruent to WX, BC is congruent to XY, and so on. We would go through all the letters. What changes ever so slightly when we talk about similarity is the following. I'm going to take the letters of each figure and write them down. If I go through this A, B, C, D, I know that I have segments AB, BC, CD, and AB, just by following the letters. You okay with that? Since it's going to be ratios, I put all of those in the numerator. The reason I put those in the numerator is because one I read first. Then I put all the corresponding ones below it. and those four are also equal, those ratios, that's what shows that they wind up being similar. In order to be similar, you have to have all angles congruent, all corresponding angles that are congruent, and all the corresponding sides have the same ratio. That for make it work. Then I hear also. So this one. That's what a similarity statement looks like. It's not real crazy, not a lot of thinking going on. It's the idea of, can you take something written out in words and put it into these ratios? Because quite honestly, what you were doing yesterday was this portion, but with numbers already given to you. Today, you're write out the letters and then put in the numbers that are in the problem. It's just adding on a step. Okay? So you did fine yesterday. This is just as simple. For example, I made it right, yeah. I'm kind of trying to write things backwards, but I'm kind of looking at the ones that I know how to write backwards. So it's going to be pretty easy. I'm a bit of an idiot. I don't know if you figured that out yet. So. I don't know if your teacher in Buffalo. Was Buffalo Grove, you said? No, it was Buffalo Grove. It was Buffalo Grove. There it is. Math teachers are always stupid and nuts. It's kind of par for the course. So what I do here is I'm given two triangles, and I'll get it for a second. Well, we have two triangles given to you. I want to check and see if these two are in fact similar, and then write out the statement. So as I'm looking at these, they're both right triangles. So you've got at least one angles that are right, correct, or congruent, one of those groups. And then the other one, I've got a single tick mark and a two tick mark. So when you go to start a problem like this to decipher whether or not something is in fact similar, it does not matter what letters you start with. I can say it's triangle CAB, BCA, ABC. It doesn't matter, as long as I use the same corresponding letters with the other triangle. Normally, you're probably looking at this going, oh, well, ABC, right? How do we all think? So if I say it's triangle ABC, what are the corresponding letters to the other one? X, Y, and Z. One right and two, one right and two. So we know that that starting point is going to work because the angles match up, the angles might be congruent. The next thing we check then is we check the lettering, and then we check the side links to see if they have the same ratio. We look at is AB, BC, AC. We write out the ratios of the sides just by following the letters of what we started with. If you keep that consistency, it's going to be really hard pressed to screw this stuff up. Now it's a matter of just filling in the blanks. What's AB? What's BC? And check those ratios. 15, 20, and 25. 15. And this is where using the calculator with the fraction bar, if you don't want to simplify it by yourself, you check to see if they all simplify to mean the same thing. As you go through that, the calculator will do the simplification stuff for you. I'm sorry, I'll dance more. What are they? What's the same ratio? 5 over 2. Every one of these fractions simplifies to being 5 over 2. So they have a, yes sir? It does, but it doesn't, it's not always going to be as clean. All right? Because you can have 7.5 over 5 is like 15 to 3 or whatever it might be. You know, depending on how it simplifies itself to go. So it's dumb luck in that case. So these guys all simplified to being this exact same ratio. That same ratio is called the scale factor. The scale factor of a similar figure, or similar figures have what they call the same scale factor, which means that they have all the same ratio on the sides. Okay. Now, as you go through this idea of finding the scale factor, as we get into a little bit later on today still, you're going to use it to find missing side lengths. And that's kind of what we get to with these things. Just like you did with congruency stuff before, you'd solve for x at some point in time, knowing what parts match up with what. It's the same idea here. You're going to know what parts match up with what, and then since they're all ratios, you're just going to do some cross multiplying. It's going to look exactly like what you did yesterday. Right? Not too bad? No, didn't think so. Same idea. This is kind of to ease you back into this a little bit. You're going to see problems like this where they give you a proportion. They're giving you two ratios equal to each other. And then they're going to say solve for one of the parts. Well, the only difference between this problem and what you did last night was that last night they gave you the numbers set up right away. Here you have to read it to get the numbers set up. So take a second, write it out so you get it. No, because we're not switching that. Yeah. So, like I say, all you have to do here, guys, is read what they're giving you, fill in the blanks. Well, that means it's 6 over something. Could I have written BC? Sure, it doesn't matter. Doesn't matter. Is 12 over 4. Well, cross multiply. Dun, dun, dun. You can do it that way. Here's where your different stuff doesn't work. Start thinking about it. You went up 6, you'd have to go up 2. Now, there's a couple of things you can do. You can go about this. What's 12 divided by 4? 3. 6 divided by 1 is 3. 2. You can think through it. 6 times what is 12? 2. 2 times what is 4? 2. There's a couple ways you can go about this. There's nothing wrong with thinking your way through a problem because sometimes you're going to be okay by doing so. Other times, you fall back on just the regular algebra of it, and you just cross multiply, and you fine as well. Okay? That's what's nice about this similarity stuff. As long as you know how the setup works, the rest of it's super easy. Okay? It's pretty easy. Do one more of those. Like I said, this is so far today. They're flying through this. So there hasn't been too many issues here. What's the only thing the extra step you had to do in this one? Yeah, you just had to figure out what that ED segment was. Where if you look at it, you've got the whole thing is 33, you subtract the 18, and what are you left with? So they're still going to use some of the stuff that we looked at during first semester when we had that segment addition, where you have to sometimes subtract stuff out to find missing parts. It's not earth-shattering, groundbreaking, crazy weirdness whatsoever. You were too busy free throwing. So. And once again, there's one of two ways you can go about doing this. You got your calculator right away, just cross multiply and solve. You don't have a calculator on you? You can simplify this ratio, 18 over 15. When you divide those both by 3, you get 6 over 5. If you do that, the math is a little bit easier. You get 12 over x is 6 over 5. Well, that's 60 equals 6x. X is 10. You can go that route or multiply it all, press the button in the calculator. You're going to get the same answer. Yes, ma'am? It's the same thing. You're doing the same thing because what you're doing is you got this value first, and then you knew that when you got that value, what did you say it was 1.2? So when you had 12 over x, you knew that was 1.2. So you knew that these two guys could do the exchange-o, change-o. There's multiple ways of doing it. Right? Multiple ways of doing it. You know how to use a fraction mark, right? Actually. Okay. Now, check and see. Check and see if you can write out a similarity statement for these two. They're asking you to check and go through letters J, K, L, and M to be similar to T, U, D, W. The first thing you always do is check your angles to see if they match. The angles match, then you write out your sides, and then you fill in the numbers to check to see if the ratios work. So try that and see if the things match up. If they do, great. If they don't, we'll talk about it. We'll talk about it either way, but you know. You're going with the idea of starting with the lettering. Follow the letters, and then fill in the numbers. It's the easiest way to do this stuff. Be really hard pressed to screw something up. What's that? That's a little bit. That is flipped. Wait, no. Oh, Oh, that's right. Yeah. Yeah, it does.
This we did.
So hopefully, you guys are okay with all the letters or the angles matched up, right? Those work, I know that. So if you go through the letters, we have 12. So I'm no math major, but I don't think that's similar either. Because you go through it, you'll notice that none of these simplify being the same. 2 to 1, divided by 8, excuse me, so you get 3 over 2, 12 over 7, and 1 over 1. That's not going to be similar. So we try to figure out ways of writing not similar, but I think the easiest thing is this. Not squiggly. I thought about this by doing it this way. If you do a squiggle with a dash, it looks like an X. So, sad face squiggly. All right, so it's melancholy squiggly. No. And then my thought maybe he kind of looks like the ghost from Pac-Man.
Oh, yeah. They get
Yeah, they do. They have mouth. Yeah. Yes. Go look it up. There's a mouth on the Pac-Man ghost. There's a mouth. They've got a mouth. It might not be squiggly mouth. There's a mouth. Right.
Yeah.
Anyway, not a very good artist. So the whole thing that allows you to do this then, and this is kind of where we're headed to. What this is going to allow us to be able to do is the following. Is that you're going to be given a similarity statement. In this case, it tells you that you have A, B, C, D is similar to E, F, G, and D. Then it gives you a diagram with numerical values. You're going to be able to solve for both X and Y in this problem by starting with, guess what? Writing the letters out. Okay. When you have a similarity statement, you always want to write out your letters of the ratios first, because then everything else falls into place. Everything else fills in the blanks. Okay. ladies and gentlemen. Always start with the letters. Follow the letters through, and believe me, it just makes everything else so much easier. When you get all that, then you start filling in the numbers from the diagram. Yeah, 5 over y. What is it? 9 and 6. Of those 4 ratios, there's really only 3 of them that I can use. I can't do anything about the side lengths of CD and GD. I don't know enough information to do anything with them, so I don't care about them. Not to say that they're not, nice and good people and whatnot. It's useless. So I know that I have one ratio that has both numbers, the 9 and the 6. That 9 over 6 can be simplified to being what? 3 over 2. So what I do here is I take the one side length that I know, I simplify it, and I use it to solve for both the missing values. Because that 3 over 2 winds up being what we call the scale factor of the object. So by having all the letters matched out like that is, with all the figure from the congruency, excuse me, the similarity statement on the left in the numerator, figure on the right in the denominator, is that stuff stays consistent throughout the whole problem. Once you get your scale factor, you just reuse it to solve for both the missing sides. It winds up being super fast. All right. Do I have to simplify the 9 and 6? No. Sometimes it's quicker to do so because it's less math than you can probably get away with in your head. But you can still use the calculator and just multiply out. So for the value of y, we get 3y is 10, so y is 10 over 3. And just leave it like that. Okay. I do the same thing. Yes, ma'am. Because fractions are much cleaner than decimals. All right, you multiply 3.33333 repeating by 4, and I'll multiply 10 over 3 by 4. See who gets it first. Using fractions is so much easier. Trust me on this one. As you get into like right triangle stuff, you do trig, fractions are where we're going to go. And you get in algebra 2, you want to stay with fractions. It just makes everything easier. Believe me. Yes, ma'am. We're not looking at anybody, so does it mean you're not going to talk? I will say leave it. I want you guys to get in the habit of leaving things in simplified fraction form. You have the multi-view calculator, right? It'll just tell you that's the answer. I would prefer that you don't use decimals. I would prefer that you. It doesn't. I would prefer that you don't use decimals. I want you to get the habit of using fractions. Ms. Jackson. No? Oh, for the whole answer? Yeah. So what you're saying is you get 5 divided by 10 over 3. What this is called a complex fraction. This is the same thing as saying 5 divided by 10 over 3, which means it's 5 times 3/10, which is 15 over 10, which is, simplify it out, you get, what is that, divided by 5, you get 3 over 2, which is the same scale factor. And you're right, Ms. Jackson. By getting this value of y, you get this crazy, what's called a complex fraction. But it's just writing fractions vertically as opposed to writing them out horizontally. That's what that is. And then the last one, when you multiply out and you cross multiply out, when you double 7.5, you get 15. And you get 5 for x. And then 7.5 over 5 also simplifies out to be 3 over 2. It's 1.5. Excuse me. Now, Sophie, you were saying about the whole idea of decimals and is it wrong? What's that? There's a time and a place for decimals, but normally, if it's something over 3, I'm not going to write 3.3 like that. I'm not going to write that as an answer. I would prefer that you don't. But then here's the thing. What happens if your answer winds up being 2.5 and your answer is 2.5? Well, let's say, what's wrong with saying 2.5 versus 5 over 2? You have to trust me on the whole fraction thing because as you go further in math, the fractions keep showing. There is time and place for decimals. There really is. I would just prefer that you get accustomed to writing. Okay. Am I going to yell at you and scold you for not leaving it as a fraction? Are you wrong if you wrote 3.3 repeated? So would I mark it wrong? Would I give you a giant frowny face? Yes. I would draw these squiggly ghost monster. Looks like a green piece of poop, but whatever. It's a green Dorito. I've got a whole whopping 6 problems for you for this evening. I know. Pace yourself. What we're going to do tomorrow is that there's a little bit more left in this section, but it's very simple. It's going to talk about maps and scale drawings, how you use that to figure out missing side lengths, and we do a little bit more of the algebra off of a similarity statement. So we're going to work a little bit more on that. As you get into 7.3, which we might start a little bit on tomorrow, 7.3 is actually really, really short. It's just all the different ways that you can show that you have what are called similar triangles. It's kind of like, remember we talked about the alphabet soup of congruency? Side angle, side, that whole thing. What is there not in math? No ass in math, that's right.
No ass in math.
So, yeah, we did that too. We just did stuff. Oh, you did? Nice. So, what we do is we talk about the different ways of similarity. It's really easy. It's a matter, a lot of times, it's looking at angle pair relationships and going through there. So, that shouldn't take us more than Thursday to get through. So. Questions?